somewhere else in the proof, right? Because you can put together any two proofs with this rule, but you're introducing a new conjunction whenever you apply this rule. So we can look at a more complex example here. We can take this proof, right? This is a perfectly good proof. We can take this proof, say of R, which is just an assumption of R. And whenever you have two proofs, you can combine them with the rule of conjunction introduction. So here is now a larger, still perfectly good proof. Right? We had our left proof coming in, which is a proof of P and S with open assumptions P, S. We have our right proof coming in, which is a proof of R with open assumption R. And we put them together, and we get a conjunction whose left conjunct is the conclusion of the left proof, and whose right conjunct is the conclusion of the right proof. Main connective conjunction. And the open assumptions of the whole thing are P, S, R. And so on and so on and so on. Right? Conjunction introduction lets you take any two proofs at all and package them together into a single proof. That's its role. It's the kind of packaging up rule. It's the, I've got multiple things and I want them to be one thing. So I bring them together using this kind of rule. There's my coffee. Do you get a sense of the kind of stuff that this rule allows, the kind of manipulations you can do at this point? Are there anything else we can clarify about introduction? Yeah. Absolutely, yes. Order totally matters. So it matters, so P and S is a completely different sentence from S and P. And when you're applying conjunction introduction, it's the left one has to come on the left and the right one has to come on the right. Right, so which sentence it is really does matter. We'll think later on, once we've got some kind of rules and we can actually have enough texture to see some things going on, we'll think about a relation between sentences called interderivability, which just means you can assume one sentence and prove the other, or you could assume the other and prove the one, right? A way to build proofs that take you back and forth between two sentences. And you'll see that if you swap the order of the conjuncts, the results will be interderivable. That is, you'll be able to go back and forth between them. But non-trivially, you have to build a proof to go back and forth between them. You can't just snap your fingers into it. It's the proofs themselves that guide you into going back and forth between them. And there will be other cases, like next week when we look at implication, where swapping the order would result in things that are not interderivable, where swapping the order there is no way, in general, to go back and forth between them. So basically order always matters, is the way to think about it. And if you want to change the order, you can do it if you can find a way to do it according to the rules, right? By building out something that actually changes the order for you. That's how you get to change the order. So the general principle is order always matters. The overall, this is probably a good place. I think I wrote this in the introduction on the Moodle, but I don't think it was in the first video. It's probably a good place to mention. The overall vibe of this unit, let's just think about vibe for a second. Obviously the vibe is going to get real weird because of all the virus stuff going on, and so who knows. But the content vibe of the unit, right, it's going to feel super persnickety and picky, and I'm insisting on these completely pointless distinctions and rules for a while. Maybe for some of y'all it might just feel like that all semester and you'll be like, oh my god, what the hell was that? But for almost everyone it's going to feel like that at the start. I promise you that's not what logic is about. Logic is this unbelievably wild, free, creative place of expression and excitement. Logic is, I love logic so much, and I'm pissed off at the virus because it's going to interfere with sharing the love of logic to some extent. But the thing I love is invisible. And so I can't just bring it in and go there it is, right? We've got to get to it somehow. And the way we get to it is through being unbelievably picky about all these little things. So everything is going to matter, basically. And kind of sorry, I promise that's not the point, but there just isn't any other way to get to it. So that's one just general vibe comment about the unit. It really, I promise you it's not I care so much about, do you write your I capital or lowercase? That's not intrinsically important. It's the way we get to the stuff that is important. The other comment on vibe, so you've got everything now. You've got all your readings, you've got all your exercises, whatever. If you want to like charge on ahead, go charge on ahead, right? We've got due dates for each thing for the week. You can't lag behind because you could really screw yourself over if you lagged behind. But you're welcome to charge on ahead if you feel like charging on ahead. However, if you're sticking with the schedule we do, just like emotional arc, right? Difficulty is going to ramp up a little bit. It'll get more and more complex. And then around the middle of the semester is the nastiest stuff, the hairiest stuff. We'll be like, oh, what the hell? Like that'll be, for those of you who are thirsting for a challenge, you will get it then. For those of you who are feeling a little overwhelmed before we get there, you're going to feel very overwhelmed during that middle bit. And then we'll come out of that and we'll tail off with actually a kind of, and now for something completely different. So like the last 3 or 4 weeks of the semester are going to be a real change of pace. They should be something, it'll be a lot easier than what we've done in the middle of the semester, but it won't just be a return to the beginning. We'll just kind of change it up and do some more kind of easier stuff towards the end. So just to give you a warning about the emotional arc, right? If you find yourself in like week 7, halfway through the semester going, I can't believe he's asking us to do this in week 7. What on earth is week 9 going to be like? Well, week 9 is going to be very different from week 7. It'll be a lot more chill. But as I say, for those of you who are thirsting for a challenge, keep your eyes open for week 6 to 8. That's when we're going to get to the stuff that is going to push you a little bit. That'll be the thought. Okay, enough about just general vibe and that, but I just want to help set expectations so that you kind of know what y'all are getting into. I saw a question when I mentioned going ahead. Yeah.
Is it like, should we all be using an exercise book to write this down? Considering we're using paper, it seems pretty inefficient to try and formulate these fractions on a computer.
It depends on how you do, right? So I'm using paper because I'm doing it kind of live here and thinking out loud and so on. You'll notice, your readings are not handwritten, right? I didn't handwrite those. You should do I use a program called LaTeX. If you already know how to use LaTeX, which few people do, great, go for it, use it. It's probably the easiest, if you already know how to use it, probably the easiest way to do this. But if you know how to use something like Word, Word has all the symbols you'll need in it very easily and straightforwardly. And you won't find it too hard to do things out in Word. If you use something else, I don't know about other things, but like feel free to do what you can to get those symbols up and running. As a last resort, you can handwrite stuff and photograph it and send it in, but like it's on you to make it legible if you're doing that, because I've been a lot freer with that in the past, and I've got some real impossible to read things coming in. So I strongly discourage handwriting and sending it in. You can make the symbols work in something like Word or whatever equivalent of that you use.
Yeah, just because there was actually a symbol that I was trying to find in Word and I wasn't able to find it.
This sounds like a good question to ask on the perusal rather than during lecture time. So we've got our conjunction introduction set up. We need also to think about conjunction elimination. So conjunction elimination is going to be the flip side. We're actually going to have 2 different conjunction elimination rules. So conjunction introduction, packages 2 proofs up. What do you do with a package? You open it and take the contents out. Right? So conjunction introduction allows us to put things together. Conjunction elimination lets us take things apart. So here's conjunction elimination on the left. And here's conjunction elimination on the right. So 2 different rules, right? The labels indicate which is which. You've got conjunction, the E for elimination, and then a little L or R for left or right. And conjunction elimination on the left says, okay, if I have a proof of a conjunction, then I can just extend that proof using conjunction elimination on the left, and I get a proof of the left conjunct of that conjunction. And similarly, conjunction elimination on the right says if I have a proof of a conjunction, then I can extend that proof with a step of conjunction elimination on the right and get a proof of the right conjunct. So whereas the conjunction introduction rule took 2 input proofs and put them together, the conjunction elimination rules, each of them just takes 1 input proof and just extends it a little. Right? They don't put anything together. They just pull out either the left conjunct or the right conjunct, depending on which rule you're using. That's the spirit of these rules. Right? So conjunction introduction pairs things together. Conjunction elimination pulls them apart again. So to take a look at an example proof, focus, there we go. Whoa, all right. Here's an example proof using a conjunction elimination on the left. We start out with this assumption of P and Q. Right, we assume P and Q, so that's a proof of P and Q with the open assumption P and Q. Extend that with a conjunction elimination on the left, resulting in the left conjunct P. Or for a slightly more complex example, you can think of this sort of proof, conjunction elimination on the right. Start with an assumption of S and T and R and Q. That's a proof of that complex sentence with the open assumption, that complex sentence. Extend it with a step of conjunction elimination on the right, pull out that right conjunct, which in this case was R and Q. So just like our introduction rules are all going to be allowing us to result in a proof whose main connective is the connective in question, our elimination rules are all going to allow us to extend beyond a proof whose main connective is the connective in question. Right? We're taking this conjunction, this main connective above the line, and eliminating it. It no longer occurs below the line. We're taking this conjunction, this main connective above the line, and eliminating it. It no longer occurs below the line. So that's the pattern. That's why they're called introduction and elimination rules. That's one piece of jargon explained anyway. Right? When you introduce a connective, it's the main connective of the resulting conclusion, and when you eliminate a connective, it's the main connective of the thing you're starting from. Right? So you bring a connective into the proof with an introduction rule, and you get rid of a connective in the conclusion of the proof with an elimination rule. Those are all the rules for this week. So these are now the ways that you have to build proofs. The only way you have to start proofs for now and for a while is assumption, just assuming any old sentence you like. Then whatever proofs you've been able to build so far, you have three rules that allow you to extend those proofs. You've got the rule of conjunction introduction, which lets you put two together into a proof of a conjunction. And if you already have a proof of a conjunction, then you've got two different options for extending it. You can extend it with conjunction elimination on the left, or you can extend it with conjunction elimination on the right. This already gives you a very lot of proofs to have. Counting proofs is weird. I don't think, well, it doesn't even matter. Yeah, I think your notes say that we're going to say we have infinitely many atomic sentences, but it doesn't even matter. Even if we only had like 5 atomic sentences, there would still be infinitely many sentences, right? Because you could just take that sentence and itself, and itself, and itself, and itself, and itself, like however many times you want it. So even with just the rule of assumption, you've already got infinitely many proofs, because you can assume any sentence you like. So if you have infinitely many sentences, you have infinitely many proofs. So you've already got as many proofs as we're going to have. The infinity in question, if you care about this sort of thing, is the smallest infinity. And even once we have all our rules laid out, still, we'll have infinitely many proofs, but it will still only be the smallest infinity of proofs. So you're probably not going to, so don't start counting proofs, basically, is the lesson here. There's too many, and the number isn't really that relative. But you do have a lot more proofs this week than you had last week, and they're a lot more interesting, or at least have a lot more texture to them. So, for example, we could now extend this with, say, a conjunction introduction, and get R and Q and P, and a conjunction elimination on the right to get R, right? You can interleave all these rules in whatever which way you want. These are building blocks, and as long as you correctly fit the slots of the building blocks together, you can build anything you like out of them. Right? So conjunction introduction, any two proofs can come into a conjunction introduction. Conjunction elimination, you need to start from a proof of a conjunction. That is, you need to start from a proof of a sentence whose main connective is conjunction in order to eliminate that conjunction. But as long as you've done that, any which way of putting these things together results in a perfectly fine proof. So those are the tools you've got to build proofs for this week. Any questions about those tools, how to piece those things together? Sweet. Okay. So, as I said, for each connective, we're going to be looking at rules that allow us to build proofs. Check. And we're going to look at a reduction procedure that allows us to transform proofs. So some proofs, not all proofs, but some proofs are possible to do what we'll call reducing to. And for this week, reducing makes sense as a word. It will actually make them smaller. Don't get too used to that. Starting from next week, reduction can make things either bigger or smaller depending on what it is. Reduction is just like a thing that can happen to some proofs. So, if you think about this proof, for example, this is a proof of P, and it's got two open assumptions. One of them is SNT and RNQ, and the other one is P. And you might think, you know, if I wanted to establish the sentence P, I was willing to take some things for granted, but I wanted to establish the sentence P. I really didn't need to go through all that rigmarole of this proof. Right? I've taken P for granted, and I've taken SNT and RNQ for granted. But what the heck am I doing taking SNT and RNQ for granted? If I was willing to take P for granted, I could have just been done right there. If what I want is a proof of P and I'm willing to take P for granted, great. I already have the rule of assumption, which allows me to take P for granted and get a proof of P. If you had that thought, that's a very good thought to have. I know some people look at these proofs that you can build up from these things. They say, well, this all seems a bit pointless. Why would I go this roundabout way? That's a good thought. Don't let it mislead you into thinking that's a bad proof. It's a great proof, right? All that matters to being a proof is being put together out of rules in the right way. And that proof is put together out of rules in the right way, so it's a perfectly fine proof. What you're noticing, if you're thinking that it's needlessly roundabout, is that it's a candidate for reduction, that it can be reduced. So when can a proof be reduced? Here's the key principle that'll stay with us. A proof can be reduced when it introduces a connective and then immediately eliminates it. So if you take a look at this complex proof, this rightmost proof up there, as you follow it down, as it grows from top to bottom, you can see there's a place where this proof introduces a connective and then immediately eliminates it. Right? We start with an elimination over here, okay. Now we introduce this conjunction here, and then we immediately eliminate it. So, right here, we have a conjunction that's introduced and then immediately eliminated. Right? We've taken our two proofs, we've used conjunction introduction to package them together, and then we've immediately taken the right thing out of the package. So what reduction is going to do is going to give us a way of just skipping that roundabout procedure. Right? So whenever a proof introduces a connective and then immediately eliminates it, that proof can be reduced, which means we're going to turn it into a different proof. And what we're going to do when we turn it into a different proof is just get rid of that connective altogether. If we introduced it only to immediately eliminate it, right? We brought it in just to throw it out. Well, then we never needed to bring it in the first place. And reduction will bring us to a proof that never did bring it in the first place. So in this case, if I'm going to put two things into a package and then I'm going to take one thing out of the package, the simpler thing to do, since I must have started with that thing, is just to hang on to it. Right? Don't put it in a box and take it out. Just, you already had it, you've got it. So in this case, the reduced form of this proof goes from this whole mass just to that, just to the assumption